All right, let's continue with shortcomings of expected value, something to be aware of. All right, we talked about this Flaw of Averages book, and here's an example. All right, imagine that you flip a coin, you win $1 if you get head a tail, you lose $1 if you get a head. Right? On average, how much money you are going to win? Well, $1 with a chance of one half, and minus $1 with a chance of one half. So zero. Average is zero. Well, what if I change this $1 to $1,000 and this $1 again to $1,000? Well, how much on average? How much you are going to win? Well, it's a one half times $1,000 plus one half times minus $1,000. It's zero again, right here in the middle, right? You see that in both cases, average tells me that from average point of view, these two scenarios are the same. I'm sure you can appreciate that there is something fundamentally different between these two scenarios. First one poses less risk than second one. Well, we haven't defined risk yet, and for that one we are going to wait a little bit, but just the general definition of risk. First one is less scary than the second one, right? How do we quantify that? How do we capture that concept of less scary or scarier than scenario B being scarier than scenario A? Well, that concept is going to be captured with variance, right? Forget about the formulas for now, even though I'm going to explain from the formulas. Let's focus on the concept, all right? So in both cases, in these both cases, you see that the average is zero, right? The average is zero. But this one, how much how far am I from average? Well, I go 1 unit this side, 1 unit that side, right? How about here? Well, from average, I can go all the way to 1,000 units to right, 1,000 units to left, right? So I need to find a way to capture distance between different values from the average, right? In other words, the values of x minus mu, right? And that's exactly what's captured by variance. Here's the problem. In this case, x minus mu is going to be 1 minus 0, 1. And then x minus mu is going to be minus 1 minus 0 is going to be minus 1. If I just simply add them up, I'm going to get 0. Same thing here. I'm going to get 1,000 minus 0 plus minus 1,000 minus 0. I'm going to get to 0. I need to find a way to avoid those positive and negative values canceling out each other. How do I do that? But I'm going to bring them to the power of 2. So far, I have x minus mu to the power of 2, right? And I want to give weight to each of those values, right? So it's going to get me to this. X minus mu to the power of 2. But each of those values of x needs to be weighted by its probability, right? And in this case, it is going to be x minus mu to the power of 2 times probability of x. Well, I have more than one value of x. I want to find the weighted average. Well, it is going to be sum of x minus mu to the power of 2 times probability of x. We call that variance. You see, it measures my distance or weighted distance from, roughly speaking, from the mean, right? X minus mu, but I don't want to cancel out negative and positive values, so I take it to the power of 2, but not all values of x have same weight or importance. So I'm going to multiply that by importance or weight time probability, right? We show that with v of x or var of x, variance of x, or sigma of x to the power of 2. Well, what is sigma if sigma to the power of 2 is variance? Well, sigma itself, if you take a square root of variance, we are going to get to standard deviation. All right, sigma of x is equal to square root of variance. Now, I'm going to, just for the sake of time, I'm going to skip this example, but I want you to try to do the calculation yourself. All right, there is going to be template in your course website. We can use that template to find a value of variance and standard deviation. Now, I'm going to skip just for the sake of time, practice problems. Now, we have talked about so far general concepts of discrete random variable, right? Now we need to focus on special case random variables. Well, those special case random variables are discrete uniform, Bernoulli, binomial, geometric, negative binomial, hypergeometric, and Poisson. What are these names? Well, these random variables are defined in a way that they show up in different practical situations. All right, so they are very special case random variables, and in different scenarios we may come back and use them. That's why they have a special name. That's why they have been studied extensively, and we are going to learn them extensively.